Welcome to my talk. This is Understanding Probabilistic Data Structures with 112,092 UFO sightings. I've actually given this talk quite a bit. It's one of those wonderful talks that's a little bit evergreen because probabilistic data structures are, well, I was going to say they're always relevant, but I don't know that that's true, but they're solved problems. It's like talking about a hash table. Hash tables work the way hash tables work. And they're one of those sort of fundamental computer sciencey things. But a lot of you probably have no idea what they are. So that's what we're going to talk about today, is we're going to talk about what probabilistic data structures are. Talk a little bit about hash tables and hashing, because principles in that sort of stuff is relevant for probabilistic data structures. And I've got a little bit of demo. I'm going to go into detail on a couple of different probabilistic data structures. And then I work at Redis. And so, of course, a couple of these are implemented in Redis. I'm going to show you how they work in Redis. Got some demo, some code. We actually have, I have a bunch of UFO sightings in a CSV file, 112,092 of them. And so the demo at the end is that I use a probabilistic data structure to do a statistical analysis of the words in UFO sightings. And by statistical analysis, I mean I count them. So that's where we're going to end up at the end. And we'll find out what the top 10 most common shapes are for UFOs. Spoiler alert, object is a shape. And we're going to find the top 10 most commonly used words that are not like stop words. It's not going to be a, and, the, but, if, those sorts of things. It's words that would actually be relevant. So my name is Guy Royse. I'm a developer advocate at Redis. I like to joke that there's three things on this slide that matter. There's something that matters to you, there's something that matters to me, and there's something that matters to my boss. So my boss would like you to know that Redis is more than just a cache. It is a memory-first NoSQL database. Honestly, I'd kind of like you to know that as well because, well, I have equity. But if you have questions about any of this stuff, of course, we're sponsoring, and so we get a booth. And so come on by. That's the thing my boss cares about. The thing that I care about are these social links here. I judge my worth as a human based on how many people follow me on social media. That seems a good way to live your life. And so give me a follow on Blue Sky, on Twitter, currently known as X, or you can go out and read my blog at guy.dev. And the thing that matters to you is that GitHub URL right there. So I've got code out there. All my talks have code. My slides are out there as well. So you can go out there and peruse my GitHub and try this out for yourself. So, 112,092. This is exactly how many rows are in the UFO sightings database that I have, the CSV file. This data is kind of amazing. It's a surprisingly large number. The records go back to about the 50s, which is kind of when UFOs became a thing. And up till, I've been using this data set now for about 10 years. So it's about 10 years old. But still, we're talking 50, 60, 70 years of data. It's it's actually a lot more than you would think. It's like well over 2,000, it's about 2,000 a year maybe, at least over 1,000 a year of UFO sightings. It's a lot of sightings. It's a lot more than you would think. The source of this data is, of course, the internet. The internet has everything. This is Tim Renner. Tim Renner is my personal hero. He is a data scientist who likes to experiment with weird data. And so he goes out and he screen scrapes these sites. The Shadowlands Haunted Places Index to get haunted places in North America. I may be doing something around Halloween on that topic. He's got a Bigfoot sightings data set. The Bigfoot sighting is great because he does an analysis of the Bigfoot sightings to find out where you can find Bigfoot. And he's got the latitude and longitude, and he looks for it. And he does a clustering algorithm to find out where do these Bigfoot sightings tend to be clustered. And he gets these kind of odd groupings. And then he lays a vegetation map of North America over top of it and realizes that you can find Bigfoot in the woods. And so he's done important stuff. And the UFO sightings database, which is it's certainly the biggest one. There's more Bigfoot sightings than there are any of these other ones. And he was looking for patterns in the UFO data. And there's a couple of interesting patterns. He did a basic histogram to see what days are most common for UFO sightings. Any guesses with the context that these are in North America? specifically in the United States, what do you think is the most common day when everyone would be looking up at the sky and they would see a UFO? The 4th of July. Everyone's looking up at the fireworks. Some kid's like, Dad, is that a firework? No, son, that's a UFO. The second biggest day was actually New Year's Eve. A lot of fireworks there then too. Lots of fun things. The nearest location geographically, like the vast majority of UFO sightings happened within 100 kilometers of a U.S. air bases. Not saying it was the Air Force, but it was the Air Force. So, but he's doing the Lord's work, ain't he? This is fantastic. This is why he's my hero. And he screen scraped all this data. Unfortunately, actually, the National UFO Research Center forced him to take his data set down, but I still have it on my hard drive. So, sucks to be them. We're going to use it anyhow. The data is actually quite fun. You've got, it's just a CSV. There's a summary of the UFO sighting. 3 saucer-shaped ships high in the sky, metallic but no shine, rather dull gray. They hovered overhead in a V formation. That sounds like a UFO sighting. This happened near Salem, Oregon in 1950 on September the 15th at, it looks like, about 2 o'clock in the afternoon. And so we've got the summary, we've got the city, the state, we've got the date and time stamp, many of which are approximate, of course. We've got the shape, things like disk or triangle or object or light. These are also shapes in this data set. We've got a duration, and this isn't like a hard number. This is like it's a human response. It's how long did you see it? For a couple hours, 15 minutes, very briefly. It's that sort of duration. It's for us humans to read. It's unstructured. It's not structured data. There's a link to the report on the New Forks website, and then the full text of the report, and then a latitude and longitude where it happened. So this is fun data. We are going to use this data to explore probabilistic data structures. Because we need to use some sort of data, and this is as good as any. We might as well use data that's fun rather than data that's boring and staid. So probably an important question to answer is, what the heck's a probabilistic data structure? Anyone heard of probabilistic data structures before? A few of you? Is Bloom filter the only one you've heard of? That's usually the answer. If you haven't heard of probabilistic data structures, then you're in good company. This is admittedly a fairly old survey. I did this in 2019. But I asked people that were following me back when this was still Twitter. You see it says Twitter web app on the bottom. You can tell it's old. Have you heard of probabilistic data structures? 60% of the people had never heard of them. Roughly 20% had. They'd heard the term. I don't know what percentage of them heard that term in the question, but I suspect it's more than 0. But so we're looking at like 80% of 4 out of 5 developers have neither heard or have only heard of probabilistic data structures, whereas only 20% knew what they were or had ever used them. Now, this is obviously just a little survey on Twitter from my account, so it's a little anecdotal. But the point is if you don't know what these are, that's how it's supposed to be. That's not surprising at all. Because these things are really interesting data structures, but there are scenarios where you need to use them are things where you need to scale in ways that often you don't have to. And we'll get into that in more detail. And it's one of those things you can kind of put in your back pocket as a trick. And then when someone says, well, how do we do this problem here? We're having this trouble. It's like, well, I got this idea. And then you can save the day. So I'm arming you to be a superhero. To understand, however, what probabilistic data structures are, I think it's first worth talking about deterministic data structures. These are the data structures that you've been using your entire career. Things like linked lists and sets and arrays and tables and trees and stacks and queues. These are familiar to all of us. And they're deterministic because they do what you tell them to. And you just add stuff to them, and then you can pull it out, and it's still there. It doesn't do anything unexpected or surprising. The order of operations generally don't matter. I mean, obviously, the order you add things into a list matters. But if you add a bunch of things to a list and then ask for the count of that list or a bunch of things to a set and get the cardinality of that set, it will be correct always. Whereas in a probabilistic data structure, it might lie and give you an error that is inaccurate. And I'm going to talk about one deterministic data structure that we've all probably learned a little bit about, but this is be a little bit of a refresher, and that's the hash table. We all know what a hash table is. We use them. We used to have to write them, but nowadays everyone just has them baked into their language. And so if you're a JavaScript developer, or if you're a C# developer, this is a dictionary. If you're a Java developer, this is a map of some variety. If you are a Ruby developer, they call them hashes. I think in Python they're dictionaries. And if you're a JavaScript developer, it's just everything. And we know how these work, right? You get a key, you get the value. You can set the value, you can get the value, you can read it. If you go and get a thing that's not there, you get null back. It's just key value store. It's kind of what Redis is, actually. And they're called a hash table because they make use of hashing functions. And the idea of a hashing function is you can give it some sort of seed number. I see a bug in my slide here because I converted it to new type. That's supposed to be 2 curly braces, not 1 there. But that's the data that we're putting into a hashing function. And we can give it a seed, a randomizer, salt. There's lots of variations. But the general idea is a hashing function is a deterministic algorithm where if you give it a chunk of data, it will spit out a number. And it will consistently spit out that number. And there are a lot of different varieties, a lot of different ways to create hashing functions. The hashing functions that you would want to use in a hash table would not be cryptographic hash functions, because those are optimized for, hey, I put data in here, and if I put data that's really similar, I want it to be wildly different. Actually, I don't even want it to be wildly different. I want it to be randomly different so that you can't reverse engineer the data by changing it. These are more keyed around performance. You want your hash table to be fast and relatively evenly distributed, but the randomness isn't as important. But you take that data, you take a seed, run it through a function, and then it spits out a number, like a 32-bit integer or something like that, that is sort of like a signature. And you can't get the data back from that hash, but the data always consistently produces that hash as long as you use the same seed. A hash table takes advantage of this capability to get a number by, say, take a key. Here we've got the key city. We run it through our hash function, and we're going to get that like 32-bit integer, or that 64-bit integer. And we've got on our right, we've got our hash table, and it's an array of lists in this particular example. And we have an array of 10 items in our list. Our array is 10 items. And so we take the word city, and we run it through a hashing function, and we get a number, and we do a modulus of however big that array is, in this case 10, and that gives us an index. And if there's nothing in that index location, then we add the thing to the linked list. And so here we've added the city of Salem, and so we add the key and the value. If we come in and add something else, say state, then that goes through the function again. We do a modulus of 10 because we have 10 items. That gives us a 4 in this hypothetical setting. And then we put state Oregon. And then if we want to read these, then we can just pull, we can reverse this. You will eventually get a collision because we only have 10 items in our array here. And so if we, say, put shape in, and we want to say the shape of a particular UFO sighting, and we get another 1, we look in there and say, well, this isn't empty. So let's go ahead and add this to it. Let's walk this list and see if it's in there or not. And if it is, then we'll update it. And if it isn't, we will append it to the end of the list. And then when it comes time to read it, you just reverse that process. I provide the key of city. I get a number as a result of this hash function and modulus. I go in there, I walk the list until I find city. If I don't find city, I return null. So this is a refresher on hash functions in 5 minutes. And this is relevant because we use a lot of hashing functions in probabilistic data structures to hash the data away and compress it down so that we can do interesting statistical tricks. When we are choosing our deterministic data structures, we are often making trade-offs between time and space complexity. Some algorithms, some structures are very, they have like an O of 1 for time versus an O of n for space, like an array. Linked list actually is more compact. Like an array wastes space because it may not be full. A linked list is nice and compact, but it's O of n to walk over it. And so you've got trade-offs that you're making when you select these data structures as to how they behave when iterated and those sorts of things. But this is actually slightly simplistic because we're not necessarily making a trade-off between these. It tends to be sort of an intrinsic quality to the data structure. So like the nice thing with hash tables is that accessing them is O of 1 because the hash function is executed and you go straight to the array element. And because arrays have an O of 1 time complexity to access things. Technically, a hash table, if you have a linked list, you got to walk, it would be slightly more than O of 1, but you get the idea. But this is a little bit of false dichotomy. It's really these traits. But there's actually a third thing that you can trade off on more than just the type of structure that you're using for time and space optimization, and that is accuracy. You can sacrifice accuracy to reduce time and space complexity. So you can make things less accurate, and they can take an orders of magnitude less space and be orders of magnitude faster, with the exception that it will lie to you sometimes. Now, your reaction as a developer to that is kind of like, no, it must always be perfectly accurate and deterministic. And I don't want things that are going to lie to me sometimes. I need perfect accuracy. Well, do you? This is a JPEG. I know it's not obvious, but this is a JPEG. This is the Devil's Tower in the Badlands in Wyoming, and if you're old enough to remember, someone made a pile of mashed potatoes out of it. None of the young people are laughing. Go watch Close Encounters of the Third Kind. Totally, this features prominently in there. In this picture, there's a pixel. See that blue pixel right there? Yeah, that one. It's actually the wrong shade of blue because it's a JPEG and it's lossy. Do you care? No, you don't care at all because you see a cool looking, piece of geology. Probabilistic data structures are like that. They're a little bit lossy, but they're good enough. You can think of a lot of probabilistic data structures as sort of odd sets. Normally a set would have, you'd be able to add things to a set, you'd be able to remove things from a set, you could get the members of a set, you could get the cardinality, these sorts of things. Probabilistic data structures are like this, except they have limited capabilities. For example, of course you can always add things to a set. If you can't add things, it's useless, right? But you might not be able to remove them. You might not be able to get the members, you might be only able to get the cardinality. Because you can know how many things are in the set, but you can't know what they are. Or you can know if a thing is in the set or not, but you can't get a list of the things that are in the set. So these sorts of data structures, they act like sets, but they're bizarre. They're limited, they're peculiar. We can test these sets for membership. Is the thing in the set? Many probabilistic data structures work this way. Bloom filters work this way. Some probabilistic data set, structures are optimized around cardinality, so they're about counting unique items. You just keep adding unique items to them, and then you can get the count, but you can never get the unique items back. Or like in the case of membership, you can keep adding things to it, and you can get the membership. You can say, is this thing in there, but you can't get the list of members back. Some are about frequency. It's about counting groups of things like count, min, sketch. Are you doing your talk on count, min, sketch? You already did it? Okay. No, you should have saw it. It was great. But you can do, you can take members of the set and see how many times they've been added. And these numbers can be a little bit off, but they can scale really well. Some are about ranking. It's not about the count, it's just the relative order to each other. And some of them are about comparing sets against each other probabilistically. This set is similar to some other set, but not this other one. And how similar are they? And you can do that in a probabilistic fashion and as well as a deterministic fashion. When it comes to probabilistic data structures, there are a lot to choose from. These are some ones that I'm familiar with most of these, but not all of them. We're going to talk today about Bloom filters, Heavy Keeper, and MinHash, not in that order. Bloom filter will be first, then MinHash, and then Heavy Keeper. If it's got that little red cross next to them, those are part of Redis. So if you're using Redis 8, those are available to you. And so Bloom filters and Cuckoo filters are all about testing for membership. You can add things to them and say, is it in there or not? Cuckoo filters will also let you remove things. And there's slight performance differences between the two of them. It's kind of an edge case to care about it. Hyperlog log is all about counting things. It can count unique items. I believe it starts getting to number of unique items equal to the number of atoms in the universe sorts of numbers. And it all fits in 12 kilobytes, which is pretty cool. But all it does is let you count them. You cannot get them back out. You've got count min sketch, and that is measuring the frequency. It's counting groups of items. It's counting various items in a set. T-digest, which is sort of a probabilistic quantile. Heavy Keeper, which is it's actually really great, and we're going to go into detail on this one. It's really great at getting, what am I thinking here? It's really good at trending topics, and so you can add things to it, and it will give you a ranking, but over time, things that stop coming in start falling off, and new things will start bubbling up to the top. And so it's a great option for trending topics. And then MinHash is about looking at, you can use it for like document similarity. So we're going to talk about 3 of these. We're going to talk about Bloom filter first. Bloom filter is the one most people know about. It is a set. You can add things to it. And when you ask, is this thing a member of the set, it will say no or probably. It can definitively say no. You cannot get a false negative. All negatives are true. However, the positives can sometimes be false. It is a fixed size when you create it. And every operation on it is O of 1. And you can scale these things up really large. This data structure is fantastic. The example I always like to give for Bloom filter is this is great for if, let's say, you're a really big company that has a bunch of users, like I say, Facebook. How many users does Facebook have? Like 1 billion? And each of those users has a unique username. Do we want to, how do we make sure a username isn't taken when you go to sign up? Do we do select star from users where name matches? 1 billion rows returned. No, we're not going to do that, right? And so you could put all those usernames in a Bloom filter. And then when someone comes along and says, hey, is some username taken? I don't want to make up a username at random. I'll probably violate the code of conduct. And it'll say no, in which case you're free to move on and just use that username. You know it hasn't been taken. Or you can say probably, and then you can say, well, let's check to be sure. Or you can just say, sorry, that username's not available. And so this allows you to scale that problem. And no matter how many usernames you put in there, that performance is always O of 1. It's O of 1 from space complexity and O of 1 from time complexity. I guess it's O of n for space complexity for the size it was when you created it. But Bloom filter is made up of a few different parts. There is a series of hash functions with seeds. They all need to be different. You can use different hash functions, but different seeds is fine. And you've got a bit array of a fixed width. A real one's going to be a lot more than 10, but this fits nicely on the screen. And the way it works is that you can add a thing to it. And so let's add some of these UFO sightings. This is a UFO sighting that is probably my favorite. It's entitled Megatron in the Bushes. You know Megatron, the Transformer, right? So these guys back in the 80s are driving along the highway, and they out in the desert somewhere in like Arizona or Nevada, New Mexico, I don't know where, and they pull over because they need to take care of an important but necessary bodily function. And so they pull over and they find a convenient bush to go walk behind, and as one of them is walking towards the bush, they hear a sound. It sounds like Megatron transforming from the Transformers cartoon in the 80s. You know, that sound. They hear it, and so they freak out. And they hop in their car and they head off down the highway, and these lights come up from behind the mountain and chase them down the highway, and they totally weren't high. Fantastic story. I'm sure it's completely true. But you're scanning through this document, it's like Megatron in the bushes, what the hell? And so you got to read it, right? You can go look in the file, it's actually in there. So we can take this Megatron in the bushes and we want to add it to a Bloom filter. We want to make sure that we're not seeing the same story more than once. And so we can run that text through these hashing functions, get 3 unique hash values, and do a modulus on the width of that bit array and get indices. And then the index, those indices, are flipped to 1 at those locations. So you got zeros, now they're 1. And then if we want to go read Megatron in the bushes, then we go through the same process, we get the same indices, and we look at all the bits at those indices and say, are they all 1? If they're all 1, then we say, yeah, that's probably in there. If any of them are 0, it definitely is not in there because otherwise that bit, all those bits would have been set. Let's add another UFO sighting to our Bloom filter. This is, I seen a UFO when I was about 13 years old. It was in all uppercase in the original text. This happened in my hometown of Columbus, Ohio. And in this particular case, we run this same thing through. We get different numbers, but one of the numbers up there, that one on the top right, is the same. The index is the same. We flip the other 2 bits, and on the rightmost bit there, we just leave it alone. And we've got a collision, but it's okay. Because if we go in and read, I seen a UFO when I was about 13 years old, we go test for membership to see if that's in there, we get all 1s back. And if we go and look at Megatron in the bushes, we get all 1s back, and they've overlapped, but they haven't fully collided. And so this is why you use multiple hashing functions. It spreads out the risk. If you get a collision, you're not as likely to get a collision on all of them. However, you can get a collision on all the ones that are set. So here we have investigators from the Bigfoot Field Researchers Organization observed a glowing green-blue sphere. And the numbers out of this one collide with all of the existing numbers that are already there. And so if we add this and then say, is this UFO something we've seen before? We can answer probably, and it'll be a true positive. However, if we hadn't added and asked, it would be a false positive. This is why they're probabilistic. A thing that can happen, you might be looking at this and thinking there's a thing that'll happen. You need to make sure when you build this Bloom filter that your bit array is big enough for all the things you want to store in it. Because what will eventually happen is everything will be 1. And then everything is a false positive. Basically, the Bloom filter becomes an American, and it's like, can we do this? And, yes, we can. 100%, always yes. and nobody wants that. So there's some math you can do to solve this problem. This slide's mostly for documentation, so you can go look at it later if you want. There are calculators that'll go out there and do it. You can make some assumptions for things and calculate this by hand, but there's really no reason to do that at all. There's online ones. When using it from Redis, it's fairly straightforward. You can just create a Bloom filter with the bf reserve command. You can give it a key name. Bloom filter is a key in Redis. You can give it an error rate. That is used, and a capacity. And those are used to go through this math back here to create a Bloom filter of the appropriate width. Redis has a feature in it where if you go beyond your capacity, it does keep a separate counter of how many things you've added, and it will create another Bloom filter and another Bloom filter and then it will go through and check them all. That's to keep you from hurting yourself, but it has a performance hit because now you've got to check multiple filters. You're better off going out and knowing, okay, I've got 1 billion users. I need something that's scaled for a billion entries in the bloom filter. There are commands to add, bf add, and you just give it the key and the item you want to add. It's a string. So disk, here we're adding light, and here we use the mad command, the multi-add, to add light and teardrop. And you'll notice these return 1s and 0s. The 1 means the bloom filter was modified. And the 0 means the bloom filter was not modified. So you can actually add something and know whether you have a duplicate or not, or a possible duplicate. So you can add and check at the same time. But ultimately, this is a fairly straightforward command in Redis. If you want to then see if something exists, you can use the bfExist command, give it a key, give it a member, and it will give you a 1 or a 0, depending on whether a 0 for no and 1 for probably. And so here and then there's a bfMexists, the Mexists. They're Mexican extremists. Yeah. I just think it's such a strange command name. I like to try to pronounce the Redis command names, like a set add command is sad, and the set members is s members or smembers. So you can make words out of all of them. It's fun. So that is bloom filters. We're going to talk about MinHash next. This is not anything that's in Redis, but I think it's really interesting. Hopefully, looks like we're doing okay on time here. MinHash is all about determining the similarity between documents in a probabilistic fashion. This was originally created, I think it was Alta Vista, created this to determine whether they should index a document again or not, so that they could look at a document and see if it had changed enough to determine whether it was worth re-indexing. But the idea here is that you can turn your documents into sets and then use those sets and do a comparison to see how similar they are. To compare sets, we can use a simple technique called Jacquard similarity. Here we have agents Scalder and agents Mulder, Scalder and Molly. They're face swapped. And they've got sets of states in the United States in which they've seen UFOs. And so Scalder has seen them in California, Nevada, Oregon, and Wyoming, and New Mexico, and Ohio. Molly has seen them in New Mexico and Ohio as well, Florida, Kansas, South Carolina, and West by God, Virginia. New Mexico and Ohio are the intersection here, which sounds legit. That'd be Area 51 and Hangar 18. To see how similar these sets are of places they've seen UFOs, you can take the cardinality of the intersection. So there are 2 things in the intersection, New Mexico and Ohio, 2 states. And then the cardinality of the union, there are 10 things. And then it's just 2 divided by 10. It's a simple ratio. And this will tell us how similar these 2 sets are. If they are identical, then it'd be 10 divided by 10. And so they'd be 100% similar. If there's no intersection at all, you get a 0. And so we can use this to compare documents. But you can't just shove a document into a set. Like, how do we turn a document into a set? Can I just take all the words in a document and put them in a set, and take all the words in another document and put them in a set, and then do a Jacquard similarity on those documents? No, that's not going to work, because all the documents have all the same words, right? It's just going to prove that they're written in English. And so if I want to build something that, for example, compares all of the term papers that you have written to see if anyone's cheated, to see how similar they are, I can't just shove the words in, because they're all going to be very similar, and you're all going to get bad grades unfairly. Whereas with some sort of other mechanism, you could actually turn these documents into sets. And so the other mechanism is called shingling. The idea here is that you turn the documents into trigrams, sets of overlapping trigrams, 3 words. And they kind of overlap like shingles on a roof. And so we create a set, which for this little sentence here, we notice to our left, further off in the mountains, a bright glow. That's the Megatron in the bushes. And so we notice 2 is the first trigram, and then notice to R is the next trigram, and to our left is the third trigram, and so on. So you get this sort of overlapped document structure. And when you have a set like this, you can do a Jacquard similarity, and now you can get meaningful things out of these documents. So here we have Skulder's report and Molly's report. Skinner is trying to determine whether they have cheated or not, if they've seen, or not cheated, but whether they've seen the same thing or not. And so he wants to see how similar their reports are. And in this particular case, I've kind of arbitrarily just took different pieces of this document. And so there's an intersection with a cardinality of 7, and there's a union with a cardinality of 11. We do the math, and we get 0.63 repeating. So roughly 64% similarity. So they, Skinner's happy, their story's fairly consistent. But there's a problem with this. You're comparing strings, it's slow, right? And if you got to compare multiple papers to each other, that gets expensive quick. And so what you can do is you can calculate a MinHash and then use that to do Jacquard similarity instead. The way a MinHash works is we take these trigrams that we just created and we run them through a hashing function. Each one of them goes through a hashing function. And then we get an array of numbers, a set of numbers for that set. And then we take the minimum hashed number, the MinHash, and add it to a new set. And we do this for however many hashing functions we think is appropriate. And now we've got a set of 3 numbers. And we're working with numbers, not strings, and there's fewer of them. We can do the same thing for Molly and get 3 different numbers. And then we can do the Jacquard similarity in these sets of numbers. And we can do this calculation once for a document. So if we're like Alta Vista and we want to see if a page has been indexed, we want to compare it to an existing page, the new page to an existing one, we can save just the MinHash without saving the entire page and do a simple comparison. Now, this shows that they are 50% similar, whereas the other one was 63.5% similar. That has to do with the fact that I picked 3 hashing functions, so my granularity is not very high. So, and this is probabilistic, whereas the Jacquard similarity is going to be more deterministic. But that is MinHash, and so that is a really good way to compare documents. Last, but certainly not least, we've got top K, which is actually, a top K is 2 data structures, a heavy keeper and a min heap. We're only going to talk about the heavy keeper aspect because it's the interesting bit. What top K does is it ranks the top K items. So you say, give me the top 10 most used hashtags on Twitter. I'm sorry, X. Okay, blue sky. And I kind of mentioned what this was good for earlier. It's good for trending topics because the way a heavy keeper works is things will fall off, it atrophies over time, and the numbers will shrink, but the ranking will remain consistent. One thing about a heavy keeper is that the ranking it's really about ranking. The count is there, but the count is always it's almost always less than reality. It can never be more than the actual, but it's usually less than. And you'll see why in a moment. I mentioned already that it's got 2 parts. There's a min heap and a heavy keeper. The min heap is where we keep track of the top K items, and the heavy keeper is where we keep track of the counts and let the erosion of values and the counts to shrink and ultimately be removed from the heavy keeper. It's where the trending topics go to die. So a heavy keeper is kind of like a lot of these other data structures. You've got some hash functions here on the left and some seeds for those hash functions. Using 3 hash functions, you might want to use more. And so you've got a sort of a width and a depth. And the depth is how many hashing functions you're using, and the width is how big these arrays are. And they're all the same size. And each array has in it a bucket, and that bucket has a hash value that was computed and a count. And then down there on the bottom, we got our indices. A brand new heavy keeper has got nulls for the hash and zeros for the count. Probably actually has a 0 in the hash. If the count's 0, it doesn't matter. But conceptually, we can think of this as a null. And when we go to add a value to a heavy keeper, say UFO shapes, here's object again. That object string goes through the hashing functions. It goes and it spits out a number. We take the modulus of the width of our array. I've just got a W there because it's presumed that this is probably hundreds of instances, buckets wide. That's the word I'm looking for, hundreds of buckets wide. And then this gives us an index, and then we will just update the count and the hash when it matches. So back here, these values are null and 0. We look in there, we say, hey, the hash is null, the count is 0, this one's free to take. And so we update the values and add our count there. So now if we go in and say, what's the count on object? It's 1. If we add again, what we do is we take object, we hash it, we get the index, we get the hash value, and we look in that index and say, hey, this one's occupied. There's a number in the hash. Is that number, the hash, the same as the hash I just computed? If so, just increment the value. And so then when we go to query it, we just reverse this process. We hash it again, look in there and say, does this hash match? Yeah. Get all the ones that match, take the count, return the largest one. In this case, they're all 2. And so we've added object twice, and we get an object count of 2 back out. Let's add a different UFO shape, light. Apparently light is a shape. Light, when we add it, has a collision. So the first 2 values, we get our hash value, we get our index, nothing's there, so we claim it. But for the third one, something is using it. And we look at it, and the hash value is not the same. So what happens? Do we just add to it anyhow? Do we ignore it? Do we reduce it? Well, we have a function that we run that determines whether we reduce it or we ignore it. And it's a probability of decay. When you create a heavy keeper, you give it a probability of decay. You give it a rate of decay. So the probability is B, or P probability is equal to B, which is a magic number that you give, to the power of negative C, which is the current value in there. So in our case, we set B to 1.05. B needs to be greater than 1, but close to 1. And then the count is to the power of negative the count. We have 2 items in our example. We do the math. This works out to a 90.7% chance of decay. And we use a random number generator. If we if we roll anything other than a 19 or 20 on the 20-sided die, then we are going to reduce that count, or otherwise we'll leave it alone. This is likely here that it will be reduced. And this is how things get removed from the heavy keeper. Trending topics stop getting hit, and so they stop going up, and other things come in and start eroding them away. And so now we have, for light, we don't have any entries for light in the bottom row. Instead, we have eroded the value for object. And if we query after decay and look for the word light, we get 1, 1, and 1. I think that's wrong, actually. I did change these slides on Monday for the first time in 5 years. But you can query for light, and then you will get, hang on, I want to make sure I say this right. Yeah, so that last one, actually, when we query for light, yeah, light created the collision. So when we query for light, we're actually only going to get ones in the first 2 rows are hit, and they're both going to be 1s. When we query for object, we're going to get hit on all 3 rows. It's going to be 2 2s and a 1 for the count. And so the count is wrong on the last number in the last row. It's less than it should be. But the top 2 are still 2, and you just take the max number, and so we're still getting an accurate count. So this allows things over time to get eroded away. This is why it works well for trending topics. The min heap, then, whenever we do one of these things, you look at the number that you have, you add something, you get the number back, or you modify it, you get the count back, and then you look at the min heap and say, is this number bigger than the lowest item in the min heap? And if it is, you add it to the min heap and reshuffle it, and now you've got your new top K. And so if you ask the heavy keeper, or just give me your top items, list them off, it's just looking in the min heap. But when you're adding and modifying that heavy keeper, the top K, it's modifying that heavy keeper structure and updating the min heap. Commands to work with it is topk.reserve. You give it a key name. You give it the K value, the number of things you want to keep track of. You give it a width, which is how many buckets you have wide. You give it a depth, which is how many hash functions you have. And you give it a decay rate. This decay rate is the reciprocal of that B in the formula earlier. So this is 0.9. So it wants to be close to 1, but not 1. When you go to use topk in Redis, you call topk.add, and this just adds something to the topk structure. Here we're adding disk, and then we're adding disk and teardrop, and then we add light and disk and teardrop. There's a query command where you can say, what is the rank of disk in topk? You can count. You can actually interrogate the heavy keeper for the count. Not super useful because the numbers tend to be lower than real, but you can go and get it. And using topk count, you can call topk.list, and it will list out the things in the min heap. So that is that. I've got 4 minutes and 9 seconds to do a demo. Do we think we can do it? Yeah. I'm not going to show the code. It's out there on GitHub, and honestly, I haven't updated the code in 5 years, so it uses a really old version of Python. But the key thing that it does here is that it does remove all the stop words. I'm using pandas. I remove all the stop words, and we're going to take the shapes, and we're going to take the words in the descriptions of the UFO title and the summary, and we're going to count them up using a topk structure. So let's do Python app.py. Please work. And I did test this beforehand. Python main.py. So app.py is just polling Redis periodically to get the counts from the topk structures. Oh, come on. Build.py. There we go. I love it when it's... Oh, and I got to start Redis. I'm using Redis 8 release candidate 1 because Redis 8 just came out on Thursday and I haven't updated yet. So come on, Redis. You've got 2 minutes and 51 seconds to load. Okay, let's try this again. There we go. Okay, so now it's reading through that CSV file, all 112,000 of them, breaking them into words and adding them into Redis. I have built a nice little web UI to see this do its thing. Helps if there's Brave. Go to localhost. 80, or is it 8,000? I think it's, no, that's not right. It's 6,000 or something, 6,001. There we go. And all it's doing, I'm bigging that for y'all. And so these are the real-time counts as they're coming in. I'm just going in and checking about every second here. You see the top UFO words are lights, light, oh, they just flipped, object, sky, saw, like, bright, one, see, and moving. These do feel like the kinds of things you would say if you saw a UFO in the sky. And the top shapes, light is winning by a significant count, followed by circle and triangle. So this is a little demo out there, and we can go out and look in Redis if we want. I don't really have time, but and see that it's updating this topk structure, and we can run those commands and see that this is really real. I'll leave that as an exercise for all y'all to do yourself. And I'm going to go and hit the last couple of slides here. But you can see that it actually is doing things. I can hear my fan going. I know it's doing things. So a little bit of call to action here. These are some resources. A lot of the material in here I learned by reading these resources. Bloom filters by example is a great explanation of bloom filters. And there's a little calculator right there that is how to calculate the optimum size for your bloom filter. A little MinHash tutorial is fantastic. It's about 10 years old. There's a white paper on how Heavy Keeper works. I read that and figured it out and implemented it so that you don't have to. The repo for all this code also has implementations of these data structures that I've written myself in various languages. The UFO sightings data set used to be at data.world. It's not anymore. But the code for scraping it yourself is. And the National UFO Reporting Center is up there at newfork.org. Blog post on Top K. It's a little old at this point, but it talks about a lot of what I talked about. You can get Redis 8 at redis.io/try free, and Redis Insight is this nice GUI client that I did not show you, but it's totally a thing you should check out. Here's the part you care about. This is the QR code that takes you to the repo that has all the code and the slides and all that great stuff. So go check that out. We've got classes on Redis, university.redis.io, and lots of information on redis.io. And we have a Discord server if you have questions, and I can answer. I'm on there answering questions all the time, as are other members of the DevRel team. So you can trust this QR code. It will never give you up, nor will it let you down and take you somewhere it's not supposed to. And so that's what I've got. I'm waiting for the cameras to go down because I know that the QR code is helpful. So my name is Guy Royse, and thank you very much.